We are Team Infinity. My name is Martin Martinez. I'm a freshman studying Course 6, Electrical Engineering and Computer Science, and Course 15, Management Science, with a focus on entrepreneurship.
I'm Brian. I'm a freshman also. I'm a mechanical engineer student, but in this project I focused a lot on the computer programming part of it. It was a really new experience.
My name is Carlos. I am a freshman in class 2017, and I'm hoping to major in course 15 Aeroastro and to more of the mechanical side.
Hi, I'm Jack Erzin. I'm studying mechanical engineering and electrical engineering, and I took on the mechatronics and systems overview for the process.
Hi, my name is Janelle Wallens. I'm a sophomore and I'm majoring in aerospace engineering.
To begin, we'll just review the objective once more. There are two aspects to the actual challenge. One was an obstacle course, which was in a pentagon shape. As you can see, 1, 2, 3, 4, 5. The main issue with this problem was focusing on how to get from point A to point B and kind of maneuver around the hoops. Whereas in the interactive challenge was a much more fun challenge, I would say, in that you had 3 different types of stations. One you had to avoid. One was a chemical station in which there were 4 balloons, and you actually had to pop them and using specific sensors figure out which chemical it was. And the third was an image pylon, which you had to kind of figure out which kind is it, and then go above and take a picture of it. And that's just a review because the last group did a great job in actually talking about the challenge. Strategy. Based on past robotics competitions we've done through our different experiences, we discovered early on that autonomous is probably the best way to go, just because we could reduce that human error. There was a huge multiplier for it, so it was a good strategy from the start. We knew it would take a lot of planning, but because of the way our team was organized, everyone had a good amount of experience in their field. So we thought it'd be an interesting challenge to take on because, as the last group said, it was such a hard thing to do. We did this using constant onboard feedback, calibration using different sensors, bird's eye image recognition. We actually created a visual image interface like 3 days. It was pretty cool in that we could figure out which one was which based on just taking a picture and kind of using advanced matrix mathematics to kind of cope and figure out the different aspects of the image and figure out which one was which. And then repeatability, which to simplify, let's just call modular code. We actually created our own library using Arduino, which was kind of simple. And what we did is we simplified to the most basic functions of the robot, something that we knew would repeat again and again and again, so that we could recycle code and make it as simple as possible. And as I said, thank God for Plan B. Manual overdrive, as we said, we didn't really change the remote too much. We can take that apart if need be. And then we also had redundant systems in that we had 2 sensors that are kind of calculating for the same exact thing. That way we could cross-check and there wouldn't really be any issues in that, okay, this sensor is saying 100 when there's really 2. Cost, budget, we saved $3. We were given $100. We were given $100 from the start, and what we did sacrifice was we spent a little bit more, but we got more robust sensors because we really wanted, with autonomous, you really need to be on point. You can't tease it as much. So we had an XB, which is a wireless communication sensor, accelerometer, gyroscope, magnetometer, which Jack is going to talk a little bit more about.
I'm glad we saved those $3. We were able to buy bubblegum with the leftovers. So on the electronic side, we had a redundancy system. So not only do we have gyroscope and compass, so gyroscope gives us iterative changes, but doesn't tell you the exact direction, but then we also had the compass telling us what true north was. And so we actually knew starting point, where we were aiming, and how much we had changed beyond that point. And we could have a voting system to check how much each one says we had gone and get like an average value. In addition to that, we had accelerometer data going in, allowing us to know like how far we had traveled by Riemann sums. We were able to add up the accelerations, 801 physics. In addition to that, we had we upgraded to a mega on both sides, so we had more analog and digital ports. From a systems overview standpoint, it gives us a little bit more RAM. We have better processing, and we definitely needed it for all the communication systems that we had. So we kind of decided very early on that we're studying engineering. We really want something challenging. Points are nice, but really testing our limits is what this is about. So we said we're going full autonomy, and we had full communication systems, not just one way, giving sensor feedback, but we could also communicate over to the copter, telling it, activate the spark gap generator, which we'll talk about later, activate the servos, things like that. So we had full I2C communication on our sensors, in addition to serial communication through XB and radio frequency transmission, sending integer values so that we could actually break down the information happening on the copter. And we had, of course, the chemical sensors, which were detecting the Windex, and that was going in through a voltage divider into the analog and digital, or analog ports.
And so I guess I can talk about the voltage regulator. It started off as a design on a breadboard, but we decided that we wanted it to be smaller so it could fit on the copter. So I was able to use Eagle software to draw the schematic and then print it and laminate it onto a copper and basically get it down to a really small size, which is really helpful. And those diagrams for it and how I made it. And then next for the chemical sensors, we wanted very interchangeable pieces, and so we decided to make a lot of them, test what the resistivity was, and then we would dope one of them with Clorox and one without, because then we'd be able to figure out which one was Windex, because it wasn't giving us as strong as a reading as when it was not. And so that's how we did that. Next, I'll hand off to Brian for the coding.
So in general, we had 3 places where processing was happening. One was on the copter, and it would receive sensory feedback and be able to send it over through the XP to the Arduino controller, which was really doing all the hardcore, crunching numbers, figuring out how it wanted to get from point A to point B and everything, and moving the toggles accordingly. And the last one was on the computer hooked up to it would receive an image from a bird's eye point of view, and that was used to identify the pylons for the second challenge, figure out which was the balloon, which was the danger one, using image recognition, which and it could also be used to, if our sensory feedback wasn't good, it could also be used to identify and recalibrate where our position was. So in general, we have our little diagram, and we have, it starts here, it powers on, and calibrates from the sensor, using a calibration sequence which would do both challenges. And then really it was using modular code, which our team was talking about. It would find the position. In this case, I was looking for a hoop. It'll get a hoop location. Calculate using what in calibration would form a function for how the toggle would respond to the acceleration. It would make quadratic models for that, and then it would use Riemann sums to actually approximate how it would be optimal to get from point A to point B, and in such a way that it would be fast, but also not way overshoot. Because the real issue is that you can't, it doesn't stop immediately when you stop it. After that, it would get into a general vicinity, like a meter or so, and we use precision movement, which would just use direct feedback loops to move it exactly where we want it to, in which case it would perform a task, like flying through a hoop and stopping on the other side, or flying, hovering over an image and taking a picture in the pylons, or hopping a balloon and counting punches. Afterwards, after it finished finding all the locations, it would return to a start location and power it off. The code was written in Arduino, which is a C-based language, though it lacks some C functions, which is bad. We modularized the code, essentially made libraries for it, so we could just keep referencing and make sure we don't have. It makes it a lot cleaner and more elegant and easier to change things. You have universal constants. If we wanted it to move faster and as fast as we could change that and make it so we have a lot of ability to make massive changes instantly, just changing one number or something. We had the transmitter Arduino, which did computation for circuit output onboard for sensory input. These were constant communication to make sure that the controller always knew exactly where the problem was. Jack mentioned we use a lot of Riemann sums to find position without necessarily having to rely on GPS, or in this case the camera, because as we know in the real world, GPS doesn't always work.
What was the camera's function?
So the camera at the beginning, it was used as, it was for autonomous pretty much, just if you wanted to have this thing fly around and you couldn't use GPS, you could use the camera and image recognition to find out where, which Janelle's going to talk about, where the image is. However, because the processing speed was not necessarily fast enough and the interface was something which would make it even slower, we decided it would be better if we didn't have it constantly reading from the camera to get its position.
Okay, and just like Brian said, I'll talk a little bit about our image processing code, and which it actually worked in the end because during the competition we weren't able to use it, but I took a picture using the camera that was set up, and I'll show you how that worked out. But basically, so we went to MATLAB, and there was like a simple code that was already made to describe how image processing works. So that was a template, but we decided that since we didn't know what the field actually looked like, we couldn't actually take a picture of it until game day, that we knew that the balloons and the chemical sensor pylons were green. And so by taking that, we were able to use color saturation to figure out where in the picture were there the most green pixels. And by using that, we could tell our drone what to do at what station, essentially. And this would allow for full autonomy for the second challenge. So basically, you could change how often you check for the resolution of a pixel. And once you find one, it basically ran through a program which would identify where that pixel was, and then it would print out a text file that we could then send to our Arduino. And it was just a bunch of numbers that we knew what meant. So like pillar 1 would just be a 1, and that would translate to knowing that that's where the pillar was with the chemical sensors.
Now, so for the mechanical side of the Phantom, that's our computer-aided design for our gimbal assembly. And so we were designing it in a way so that we would keep everything compact and in the center of the Phantom and right below it. So then the plate with the X, the big X on it, that's attaches right into the Phantom, and right under that would be our Arduino and our electronic thing. Yeah, so that was the one that attaches right on the Phantom. And then from there, it would hook up with 4 screws on the ends, where what the holes are, and it would go to the infinity plate. And from that one, we would put the 2 side plates right here that would actually go to our GoPro assembly right here. And we didn't want to use the GoPro assembly that came with because we thought it was too heavy and too hard to work with. So we actually ended up making our own and attaching a servo on it, so we could actually rotate it on the bottom, so it could look straight down on the field when we wanted to for the autonomous system, and it would come back 90 degrees and look straight out, so when we wanted to like fly it.
In addition, we kind of went with a sandwich design where the electronics bay was actually sandwiched. It's kind of like ripped apart from so many crashes recently. We kind of went crazy with it after our competition was over. But the electronics bay is hidden within the inside, and actually all the electronics, despite all the crashing, still works perfectly because actually by sandwiching it together, you're keeping all the pins in place. There's absolutely no degree of freedom to pull anything out. So we had a very robust system for keeping everything in place.
And since it was simple design, we could just take it out in case we missed a wire, we had to put another wire, or like we had to do in the end, make it piloted. We were able to like take out the 4 screws on the end and just take out the top and just rewire the whole thing.
Okay, so from a system overview standpoint, I can kind of show what systems we created to pass the communication signal and to get all the sensory feedback and the analog digital controls. So we have on here an Arduino Mega. It's controlling the sensors, like I said before, and then we have loaded on the top an XB communication circuit. In addition to that, for the power constraints, we have the 11-volt system running in here, a 5-volt system to regulate for our spark gap generator with a 5 to 10,000 volt transformer, and then we have 2 9-volt systems. One running the Arduino and one running the transformer. The reason we have 2 separate systems is because, well, this thing pulls 2 amps continuously to create the spark gap, and we didn't want to pull from our control system because it would fly out of the sky, and especially the giant peaks in current. And we'll show right now the voltage transfer. It seems like what people have enjoyed the most out of our system so far. This system here runs from 5 to 10,000 volts to actually ignite the balloons. And if you saw in the video, I just went up to it, pop, pop, pop. You have to fly over, poke it a bunch of times. But in addition, for the funsies, we threw blades on it. It works as an electrode too, but pops and shocks at the same time. It's a pretty robust system. I mean, you just touch the balloon with this thing, and it pops immediately.
And so this is our computer-aided design for the toggle board. So then I designed the four things which we attach to the servos, and then each one of those would control the X and Y axes on the controller, which would then transmit that information through an XB, and would then transmit from that XB to our XB on the Phantom and coordinate it like that.
One of the nice things that we have here is an actual sliding rail system. So there's this huge problem in mechanical engineering, which is like the rolling joint problem. Like, how do you control 2 axes simultaneously? And that's one of the reasons like you don't see those exosuits like Iron Man flying around, is because how do you mess with this joint when you can only spin on one plane? So what we actually were able to do is we created a sliding system here. If you can kind of see, one axis can pull and the other axis can pull, and you can actually get all the degrees of movement by having one slide along the other. So we're actually able to control the full gimbal, or the full control system by having this sliding rail system. And you would think, oh, well, there must be a lot of play in it, but actually the control was more accurate than we could actually get back from like the sensors and the actual drift from the copter. So this was actually one of the more accurate systems on board. And it's funny going from digital mechanical to digital again, but it helped us avoid ripping apart the controller and possibly losing an electronic system that could not be replaced.
So yeah, so the taser is a really pretty and very simple thing to do. You just take a 9-volt battery, run 2 wires on this, on the positive and negative ends, run it through a transformer, and then just bring it to the front. And of course, we just had to replace first.
And we also put a relay module on the inside, so we have digital signal being bounced to the relay module, which is activating the low voltage side, which is then running to the transformer to the high voltage side. We thought about going with the transistor, but we didn't want to overheat it, switching transistor. But it's actually a very simple and powerful system for a problem that I didn't see a lot of teams be able to actually pop those balloons, because the balloons had the tendency to waver and move every time you impact it. But if you have just a slight touch and then 10,000 volts of electricity, all your problems go away.
It's our weapon of mass destruction.
Okay, so results and conclusion. So from looking at the overview, we had a lot of complicated systems that we were able to accomplish in a very small time span. When you look at it, we had visual recognition done. We had a mechanical system for autonomy. We had a very complicated feedback loop system taking all the gyroscopic and sensor data and feeding it through XP communication over to our main control tower. It was actually a very, I have to say, elegant and beautiful system, even though it's kind of torn itself apart after enough crashes. We had essentially autonomous working. Now, of course, the day of, just because of how things work out, one of our servos actually blew out, and I wasn't able to get a replacement until recent, so our autonomous system, by losing one axis, we couldn't run it because startup procedure needs all 4 servos to activate at the same time to start the controller. So we lost that system the day of. We also had a byte error in the communication system, so that our data was getting shifted a little bit. We, of course, have figured both these problems out after game day, but from an engineering standpoint, everything was really solved. We just, I don't know, luck.
Moving on. Before we thank our corporate sponsors, I'd just like to reiterate what each member worked on. Carlos and Jack worked on the mechanical aspect, Janelle on the aero, astro, the visual recognition, and the chemical sensors. And then Brian and I worked on a lot of the programming. I focused on the logic, and I also worked on the image recognition, and Brian focused on the algorithms and all the complicated mathematics. So we were the architects of the software, mechanical, and then she kind of told us what should be happening and what it's not. We'd like to thank our sponsors, because really this couldn't have been possible without you. Our failures today are great successes tomorrow. So I really want you to think about that and pat yourselves on the back. Take yourself out to a good dinner night. A good one. And special thanks to Lockheed Martin. You guys are representing today. There's a lot in the crowd. So whoop whoop.
Thank you so much for your time.
I have one question. So let me ask, how much did you guys move out of the comfort zone of what you already have sort of strengths in? Did you try to do
So I can speak.
you hadn't done
I mean, we can go one by one.
Yeah, that'd be great.
Okay, so I definitely moved out of my comfort zone, because even though this is a Course 16 project, there's not as much Course 16 things involved. There are a lot of electronics involved. So I really moved out of my comfort zone by going from only knowing how to do circuits on a breadboard to fully making an actual circuit that I could carry around. I had to learn Eagle software to do that. And with MATLAB, I had always used it more so for equations and functions that just calculated things and print like a graph. I had never done visual recognition before, but after just studying it for days and days and working on it all night, we finally got it down to a way that it could work. And so that was a great accomplishment I got out of this one.
So for me, I'm kind of a mechatronics person. I'm majoring in mechanical and electrical. And so starting from day one, it was like very simple. Okay, how are we going to do the communication? How are we going to do the electronics, power system? The mechanical side was not too difficult from an early standpoint. We kind of knew where we were going. We went with it. It all kind of came to fruition. But the real difficult part, I think, in my opinion, was sometimes like communicating with what our software limitations were. So sometimes, you know, okay, I know what I can do hardware here, here, and there, and then I can throw it together, but then from a software standpoint, we run into the issue of, oh, we can't do that sort of processing. Oh, we can't bit bang at that rate. Oh, we can't, you know, take that sort of sampling. And even though I had some experience with it, we really got a more intimate feel for some of the software limitations, which it's funny because you always hear the other way around, but I've really learned a lot of the software limitation stuff.
My biggest stress was time. As you saw, I wasn't in the initial video, and that's because I had prior commitments. This last week, I wasn't here at all, and the week before that, I was here about half the time. So I actually designed a lot of the autonomous in the start. So the first 2 weeks, I was pulling all-nighters all the time because I had to think ahead so much of what was going to happen that I had to come up with all these problems to kind of try to solve them before and let them know. Visual recognition, I was the initial lead on it, and I tried 5 different ways, I think. And I was like, just going through all of it, but I was really trying to expand my horizons and try different aspects. For the programming side, I kind of try to make a masterpiece. I don't know, I talk a lot about elegance and modular code. That was something that I learned little by little, and I kind of just pieced it together all right now because it just made it a lot easier, and I thought it'd be a very good exercise in how we did it. And also on the mechanical side, like Jack was very good at knowing what all the sensors did, and it's his game. I was more of the software side. So we kind of switched roles in that I think more like a mechanical guy now, and he thinks more like a software guy now. So we kind of go in, and we were this group that like, oh, can you do this by tonight? I think it would take 2 weeks, and he's like, nah, I can do this. And it was the same for me. So it was just a lot of fun working with this team, and it was a well-balanced team, so the OME helps out a lot.
Amazing sort of synergy there by the end of it. I mean, we were pulling all-nighters, kicking out stuff I didn't think could be kicked out in a night. I mean, stuff that was taking me weeks before to make it.
And we did all this under a huge time constraint. Like I said, like a lot of the hard stuff was done in the first 2 weeks.
So, just again, I'm Brian. I'm undeclared, but I was thinking strongly of doing mechanical engineering, and definitely taking a look at this. I mean, I know that Jack was before; he was a great, mechanical engineer, doing patent, whatever. And so I was, I had programming experience, and I decided to, so I said I can do help coding. I was originally like secondary coder and was going to be helping out with like mechanical systems, and I ended up, because the image processing, we originally didn't have the bird's eye camera, and so the live stream of like from the GoPro, there were a lot of issues for tying up my key, and so it actually turns out that I ended up like writing without just like the running systems for our thing, like and it was it was really interesting perspective on like how the code actually works beyond just writing methods. You have to figure out how they're going to interact with each other and really work together as a whole. And this just made me think a lot more about maybe, I also helped with image recognition, like there were bugs we couldn't figure out the last day, and it was just like all night working on it. And the stuff which now I'm thinking maybe, I might even not even go into mechanical engineering, or maybe to take a hybrid of mechanical engineering.
So I'm Carlos, and although I had a lot of mechanical experience, I was like able to bring up mechanical really fast as the project became more electrical. As you can see, like 2,000 wires, almost camouflage gimbal. So I actually took a step and took a challenge to myself in going to the electric field because I had almost no experience with wires, and I was like, what is this possible? I could have almost like burned the whole thing up. So, but in the end, I was able to help Jack a lot. He helped me out, learn a lot about the electrical components, and then I was helped out to connect the Arduino to the XPs and to the whole assembly.
Yeah, and I'd like to reiterate about the synergy. Like we consulted each other on a lot of different things. We each knew a lot about a little thing, but because of the way the challenge was, we always had to be in constant contact with each other. Like, okay, I don't know this. Does anybody know this? He's like, oh, you know that? Okay, we should do that then. So it was a great back and forth, and it was a lot more like the real world, and it's very interesting for this freshman year. Like you're just doing all the math and science, which I mean, like I love, but that's because I go to MIT. So. It was a great experience, and just like we're actually working on something, we're each using each other, and we didn't think we could even do something close to this at day one.
Any other questions?
Thank you, team.
Thank you.